Set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we are able to optimize this scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. We first show comparisons to top-performing methods on synthetically rendered data. Scene representation networks implicitly represent a scene using a fully connected neural network. SRNs have issues with multi-view consistency and are unable to represent high-frequency details. Local light field fusion uses a pre-trained network to promote each input view to a high-resolution 3D volume. Inconsistencies between adjacent volumes causes flickering artifacts. Neural volumes encode a scene as a 128 cubed voxel grid and use a warp field to better allocate these limited samples. However, they are still unable to represent high-resolution content, such as the fine details in the ship's texture and rigging. We see the same trend in all of our synthetic test scenes. Our method both qualitatively and quantitatively outperforms the other methods. Here we show the results of our method on the 6 other objects in our realistically rendered dataset with complex geometry and non-Lambertian materials. Next, we will show comparisons on real scenes, captured with a forward-facing phone camera. SRN uses a recurrent network to ray march through encoded scenes, resulting in an inconsistent appearance between rendered views. LLFF blends between multiple renderings with different limited fields of view, resulting in flickering artifacts along image borders. Here, only our method can represent fine details with complex occlusion effects, such as the ribs in this fossilized T-Rex skeleton. Now let's take a look at some additional real results.